Alright, I apologize in the break in the video. I'm still having the problem where it just stops recording video, and I thought it's because like my computer goes to sleep. I turned off the screensaver. Done everything I could. I move the mouse frequently when I'm recording these videos. I don't know what makes it stop recording. Okay, so I apologize for the breaks in the videos. I really do. Well, anyways, this is a continuation of the previous video. We had this limit. All I did was I was rewriting it up here before the video cut out, okay? So it should be up here. Nothing has changed. So we were at the point when we evaluated this limit, we got 0 over 0. So now what we have to do, we have to take the derivative of the numerator. So if you remember how to take the derivative of an ln function, it's 1 divided by whatever's on the inside. 1 minus 1 over x times the derivative of the inside. We're going to have to use a chain rule. So the derivative of 1 is 0. The derivative of negative 1 over x, well, I can write that as negative x to the negative first, and just use a power rule. Negative 1 times this negative is a positive, then drop 1 power, it'd be a negative 2. So this is times by x to the negative 2 power. I'm going to rewrite this as 1 over x squared, though. There's a reason for it. Times 1 over x squared. So we don't need this. So this was the derivative of the numerator. Now, divided by the derivative of the denominator. Hey, we just took the derivative of this, but without the negative sign. So this is negative 1 over x squared. But now look at these two factors. These two factors are just going to cancel. So let's write what we have. Limit as x goes to negative infinity of, here's this negative sign. I'm going to write it way out front. Negative 1 over 1 minus 1 over x. So now let's go ahead and plug negative infinity in here. So we get negative 1 over 1 minus 1 over negative infinity. Well, 1 over any infinity is 0. We get 1 divided by 1, which is 1. We get a negative sign out front. This limit is equal to negative 1. Okay? So this came out to be infinity times 0. So we rewrote it. So we got 0 over 0. And then we took the derivative of the numerator, divided it by the derivative of the denominator, simplified, and then evaluated the limit to get negative 1. Okay? So that was indeterminate products. A lot of indeterminate products require you to put something on the denominator, like we did in both examples. Okay? Now we're going to go on to indeterminate differences. So indeterminate differences. Why only a difference? Why not a sum? Well, let's think about it. If we had infinity plus infinity, well, that's going to equal infinity. Like a positive number plus a positive number must equal a positive number. Negative infinity minus infinity, or negative infinity plus negative infinity, this is a subtraction, this is written as an addition, is equal to negative infinity. Okay? So a negative number minus a number is still negative, or a negative number plus a negative number is still negative. Okay, so we're good there, but what happens when we do infinity minus infinity, which is the same thing as infinity plus negative infinity? Indeterminate differences. Which infinity is bigger? Is this infinity bigger, or is this infinity bigger? It definitely matters, because if you think how you add negative numbers or how you subtract numbers, well, 4 minus 7 is equal to negative 3, so this one was smaller and this one was bigger. 7 minus 4 is equal to 3. So as you could see, we run into a problem with the subtraction. We need to know which infinity is bigger, so we know how to tell our answer. Is it going to be negative infinity or is it going to be positive infinity? So this is an indeterminate form because we cannot tell whether it should be positive or negative infinity. So what do? We're going to rewrite our problems. in a form where we get 0 over 0 or infinity over infinity and use L'Hopital's rule. So here's our first example. Limit as x goes to 0 of cosecant x minus cotangent x. It may be a little bit easier to evaluate this limit if we wrote it in sines and cosines. We're going to have to do that anyways to simplify it. So limit as x goes to 0 of 1 over sine of x minus cotangent is cosine x divided by sine x. If I plug in 0 into here, I get 1 over sine of 0, which is 0. Or sorry, which is not 0, it's 1 over 0. Minus, we get cosine of 0 over sine of 0. Cosine of 0 is 1 minus 1 over sine of 0 is 0, which is infinity minus infinity. This is in a limiting sense. 1 divided by 0 is infinity. So, which infinity is bigger? I don't know. Okay? So what I'm going to do is I'm going to subtract these. I'm going to find the least common denominator. I'm going to put them together. Luckily, they have the same denominator, so this is fairly simple. Limit as x goes to 0 of 1 minus cosine of x divided by sine of x. Okay? Now if we go ahead and try evaluating the limit, we get 1 minus cosine of 0 divided by sine of 0, which is 1 minus 1 over 0, which is 0 over 0. Now that I have the limit in a form of 0 over 0 or infinity over infinity, I could use L'Hopital's rule. So limit as x goes to 0, that's the same thing, 1 minus cosine of x over sine of x. So our original problem is equal to that limit just by algebraic manipulation. So, since I already showed that this was 0 over 0, I could use L'Hopital's rule. So, derivative of the top. So it's still limit as x goes to 0. The derivative of the numerator, derivative of 1, gone. Derivative of negative cosine is positive sine of x. Divided by derivative of sine of x is cosine of x. Plug in 0, sine of 0, cosine of 0, that's 0 over 1, or in other words, 0. So the limit to our original problem is equal to 0. Okay? All we did was show that this was an indeterminate form, rewrite it in a form where we get 0 over 0 or infinity over infinity, so we can use L'Hopital's rule. Took the derivative of the numerator, took the derivative of the denominator, then evaluated the limit, and got 0. Okay? Let's go ahead and do another example. This is an indeterminate difference. This is limit as x goes to 0 from the right of 1 over x minus 1 over e to the x minus 1. Okay, now we're doing a right-handed limit. Nothing changes here. It's just saying it has to be from the right, because without this piece, the limit as x goes to 0 of just this term, it doesn't exist, because if you look at the graph, it goes up to positive infinity from the right, it goes down to negative infinity from the left. The limit doesn't exist. So that's why we're only doing a right-handed limit here. But nothing changes. How we go about the problem is exactly the same. Let's see, we plug in 0 right here. We get 1 over 0 minus 1 over e to the 0 minus 1. That's a really bad e. Let's see, let me fix that. Well, that's 1 over 0 minus 1 over e to the 0 is 1. 1 minus 1 is 0. We get infinity minus infinity. So what I'm going to do is I'm going to find the least common denominator. I'm going to put the two fractions together. So if you notice, the denominators are completely different. So the multiplication of the two is the least common denominator. So it's x times e to the x minus 1, or that on the denominator. On the numerator, e to the x minus 1 minus x. I did that pretty quickly, but if you go through the work and check it out, this is what you should get. Now, do not cancel this term and this term. You cannot cancel this e to the x minus 1 and e to the x minus 1. That is mathematically wrong right there, so don't do it. Now let's go ahead and plug in 0. Well, e to the 0 minus 1 minus 0 divided by 0 times e to the 0 minus 1. Well, e to the 0 minus 1, we already know that's 0. So on top, 0 minus 0 is 0, divided by e to the minus 1 is 0. 0 times 0 is 0. So we have it in the correct form now. We got 0 over 0 when we evaluated the limit. So now what we have to do, I'm going to rewrite that up here. I'm going to rewrite our simplified expression. Now I have to find the derivative of the numerator. The derivative of the numerator, limit as x goes to 0. Well, derivative of e to the x is just e to the x. Derivative of minus 1 is a constant, goes away. Derivative of negative x is minus 1, divided by the derivative of the denominator. I have to use a product rule. Derivative of the first one, which is e to the x minus 1, plus, or derivative of the first one times the second one, which is just 1 times e to the x minus 1, plus the first one times the derivative of the second one, which is just e to the x. Let me go ahead and take the limit now. I plug in e to the 0 minus 1 divided by e to the 0 minus 1 plus 0 times e to the 0. Well, from the previous steps, we know e to the 0 minus 1 is 0. E to the 0 minus 1 is 0. Plus, this is 1 times 0 is 0. We got 0 over 0 again. Alright, so all that means is do L'Hopital's rule again. So I'm going to erase. We already got 0 over 0. So this thing, limit as x goes to infinity, e to the x. The derivative of e to the x is e to the x divided by derivative of negative 1, done. Derivative of e to the x is e to the x, do not cancel. Derivative of negative 1 is just 0. Apply the product rule here. Plus e to the x, derivative of the first one times the second one, plus the first one times the derivative of the second one. Okay? Now, if we were to simplify a little bit, limit as x goes to infinity, there's e to the x on top. If you notice, they all have an e to the x that I could factor out. Oh, I wrote infinity. The limit should be going to 0, not infinity. I could factor an e to the x out. I'm left with 1 plus x, which is 2 plus x. The e to the x and the e to the x cancel. And lastly, I get limit as x goes to 0 of 1 over 2 plus x. So as you see, applying the L'Hopital's rule over and over and over, you eventually get something that works. If I plug in 0 here, I get 1/2. So that is the limit of this original problem right here. Again, we first plugged in the limit, got infinity minus infinity. So we combined the two by finding a least common denominator, putting together the numerators. Evaluated the limit, we ended up getting 0 over 0. So we applied L'Hopital's rule one more time. We simplified it, and it gave us something that we could apply the limit and get the answer to, okay, which was 1/2. So that was indeterminate differences. Then we got one more to go through. indeterminate powers, okay? I mentioned to you guys that this course was algebra intensive. Here's where you need to use your algebra to go ahead and rewrite these expressions. So limit as x goes to infinity of x to the 1 over x. Oh, indeterminate powers. We didn't go over that. A little introduction. Indeterminate powers. Those things are like infinity to the 0 or 0 to the infinity. Okay? We know that infinity is a very large number, but any number to the 0 power should be 1. Like 2 to the 0 is 1, 4 to the 0 is 1, 26 to the 0 is 1. But infinity is such an odd number. Infinity to the 0 can't really define what it is. 0 to any power is 1. But what about 0 to the infinite? Or sorry, 0 to any power is 0. It's not 1. 0 to any power is 0. But 0 to the infinite power. What if we have a bunch of zeros multiplied to each other? Is that should that be 0? Just like infinity to the 0 power. Should that be infinity or should it be 1? Okay? We don't know. We cannot define the actual number. That's why they're indeterminate. So when you end up with something like this, what you want to do is algebraically rewrite it so you get infinity over infinity or 0 over 0. Infinity to the 1 over infinity is equal to the infinity to the 0 power. So this is an indeterminate form. Now, how to handle these? What you're going to do is you're going to rewrite these as e to the ln of whatever this function is. So x to the 1 over x. The reason being, if you recall that e functions and ln functions are inverses of each other. So this is really equal to x to the 1 over x. All we're doing is rewriting it in a different form that is equivalent to its original form. Just like we could write this as ln e to the x to the 1 over x, like that. Okay, we could do that. Now the reason why we're going to do it this way instead of this way, both of these are equivalent, they're equal to this, but we're going to use this one because since this has a power and it has an ln, we could use log properties. We could bring that 1 over x out front, and that's exactly what we want to do. So I could rewrite this as e to the 1 over x times ln of x. Or another way of writing e to the ln of x over x. So, let's see. Our original problem is equivalent to the limit as x goes to infinity of e to the ln of x divided by x. Now, we have to use a property that we came across in chapter 2. Since e is a continuous function, it's an exponential function that is continuous and differentiable on its entire domain, what we can do is absorb the limit up into the exponent. Limit as x goes to infinity of ln of x over x. So let's go ahead and evaluate that limit instead. Limit as x goes to infinity of ln of x over x. We get ln of infinity divided by infinity, which is infinity over infinity. Hey, look at that. Exactly the form we needed it in. Let's go ahead and apply L'Hopital's rule. Limit as x goes to infinity of 1 over x divided by the derivative of x is just 1. So this is just the limit as x goes to infinity of 1 over x, which is 1 over infinity, which is equal to 0. This right here is not my answer, though. Okay? Look where we got this limit from. It was on top of an e. So this is equal to e to the 0, which is equal to 1. So this limit right there was equal to 0. You put it back in, evaluate the e, and it gave you 1, okay? So this limit right here is equal to 1, okay? And that's the end of section 4.4. Where you might find this stuff useful is finding horizontal asymptotes, because sometimes that very first example that we did where we algebraically manipulated the x minus 3 and then the x squared minus 9 and canceled some stuff, sometimes that algebraic manipulation is difficult, where taking derivatives is probably easier than the manipulation.